Okay, so that's about the different chapters in the organization. So let's take a quick look at the syllabus and see how the summer syllabus is organized. Okay, and then sometime today, before it's too late, before tomorrow or the day after, what you want to do is to test your access to homeworks. Okay, you definitely want to make sure that you have access to homework one is already available. As a matter of fact, all the homeworks are available already on Moodle. You want to test your access on Moodle. And I did talk about videos on Moodle that you should watch before the class. Now, the other thing is Triple 108L also has a Moodle page, and it's all set up and ready. I'll just make it. It's just a matter of making it available to you. Um, Tomorrow in class, in time for the class, is when 108L will become available, and you will see an email from me with a access code to sign up or enroll for this on Moodle. Okay, you want to make sure that you enroll into 108L as well. All the web page has already been developed by Professor Headley, and he has been kind enough to share his material with me. Okay, so let's take a quick look at what this course is about. Okay, and this day and age, and for the foreseeable upcoming semesters, the office space is more or less irrelevant. The fact that there was a time I used to live almost in 3010. There was a time when I thought paying rent was a useless thing because I spent most of the time in the Riverside Hall. Now that's history now. It's all virtual. The class, as you know, is online. And the hope is that I should be able to record this, and it's only going to add on to what has already been uploaded to media site videos. Okay, so the best way to reach me would be through email. And all the material here has been developed by Professor Headley, so special thanks to him. Now, here is the enrollment key for 108. There'll also be an enrollment key for 108L. I'll let you know when that is available. Okay, the textbook is the Bible in microelectronic circuits by Cedra Smith. I don't impose that you buy this, but it's a very good book to have handy. Okay, there's no way for me to impose, and it's not like me to make students buy what they don't want to buy. Okay, but I recommend it. It's just for you to decide. Okay, the course mostly talks about semiconductor devices. Okay, talks about diodes, bipolar junction transistors, field effect transistors, all the kinds of good electronic components, operational amplifiers, so on and so forth. So these are the building blocks of modern electronic devices. If you think about field effect transistors, FETs, okay, you pick up your iPhone, you pick up your iPad, any of your smart devices, your laptop, the processor in there, when they say there is billions of transistors in there, what exactly are they talking about? Well, they're talking about these MOSFET transistors that form the basic building blocks of modern electronics. Okay, fundamental building blocks in modern electronics. Okay, so we are going to demystify what is sitting inside your phone, or at least a big picture look at that, and how they operate at the fundamental level. Okay, but then there are a lot more concepts we have to understand in order to fully understand the operation of the phone. But at the basic, very fundamental level, it's the FETs that are sitting in there, field effect transistors. We'll see what they are. We'll see how they operate as different electronic components. We look at operational amplifiers, DC biasing, small signal models, so on and so forth. A very interesting set of problems and design considerations. That is what we are going to go through in this course. And all of this is um, about semiconductors, electronics. Okay, so basic building blocks of electronics, and this is an online course. Okay, and you know all about Moodle. If you don't already have access, make sure you gain access to Moodle. So here are the course objectives. You want to, by the end of the course, you'll have a set of tools necessary to analyze circuits using operational amplifiers. Okay, it's a basic building block of many applications: filters, multiplier circuits, so on and so forth, amplification circuits. You'll also use diodes. You'll understand MOSFETs, BJTs, and then apply basic principles used in power supplies and voltage regulation. So here is the grading breakdown. Homeworks. The big chunk, as you can see, is the exams. There are 2 midterm exams, each worth 30%. There is one final exam, which is worth 30%. So a big chunk of your final grade is actually the exams. And then there is some homeworks. Okay, there's some homeworks that you can take any number of times. Okay, you can take these homeworks any number of times, and there's no reason why you should not aim for a perfect 10% on the homeworks. Okay, you can think of that as free giveaway points. Okay, so for each topic, students will take an online quiz, and this is on the material covered in the class, and this is using Moodle. Okay, each quiz ungraded can be taken as many times as you want. Okay, and then only the highest is counted. The highest, when I say quiz, I mean homework and quiz. Okay, I use them interchangeably. I use these 2 terms. Okay, the 2 midterms and final exams will also be taken online using Moodle. Okay, one note of caution is that you only want to pay attention to your raw scores in your quizzes and your exams. Sometimes Moodle does show some calculated columns like the total or something. Don't pay attention to that. Moodle is not doing that in keeping with this rubric here. Okay, so the only things that matter are the raw scores that you scored in the quizzes, the midterms, and the final exam. Don't pay attention to the total column thrown out by Moodle. Questions, please.
Yeah, in like final exam, it says not comprehensive. Like what?
Yes, I'll talk about that. Why don't I talk about that? I'll address that in a minute. Okay, now that's a good question. So there are some course policies that you want to be aware of. I'm not going to read them all out to you, except talking about this. Okay, number 8. If there is somebody who needs special accommodations, extra time on the exam, or hard of hearing, or any other accommodations that you want to convey to me discreetly, you can always get in touch with me. And there's also the Student Disabilities Services Center on campus. You can get a documentation from them, so I can make special accommodations for you. Okay, now, and I ask that you familiarize with the course policies here, and all the grading will be done in line with the policies outlined here. Okay, so here is a week by week breakdown, and if you care about the chapter numbers in the textbook, that's there as well. So first week we are mostly going to talk about chapter 1. The second week is when we'll talk about operational amplifier circuits. Then we talk about diodes, MOSFETs, bipolar junction transistors, and then use these bipolar junction transistors and field effect transistors to build some interesting circuits, amplifiers. Okay, that's the idea Um, that's the outline for the course. So when it comes to exams, okay, maybe I have some more, yeah, right here. Okay, so the idea here is that here is a day by day, week by week, daily breakdown of what I expect to cover here, and the corresponding lab as well, list of topics and the labs. Okay, so the midterm one, that's scheduled for the 4th of June. First midterm is scheduled for 4th of June during the class time. So there is no way you are going to you are going to need to. There's no way you will need to or miss the. You cannot make it to the exam because it's scheduled in the class time. Okay, so the class time is a midterm, and it's only from chapters 1 and 2. The second midterm is on the 18th of June. These are in quick successions. This is a summer course, very busy time, short semester, 6 weeks. That's scheduled for the class time as well. And it's not comprehensive either. It's only covering chapters 3, 4, and 5. Okay, and then the final exam too. That's not comprehensive either. The final exam is scheduled for the 2nd of July. Okay, for the class time, and then I think it's a 2-hour exam. I don't. I can double check on that for you. But the idea is that this is not comprehensive either. It's only on chapters 6 and 7. Did that answer your question from earlier?
Yes.
Okay. So that's about the schedule tentative. This is tentative list of topics that I will be covering, and then the exam times. Okay, what you want to pay attention to is this guy. It's a color-coded document. Okay, it's a color-coded document, and the point I want to emphasize is that the schedule is weaved around, created around these exam deadlines. Okay, so if you look at the exam, midterm exam 1, which is on 6/4, then look up, look on the rows above it, you'll see that 3 quizzes, quiz 1, 1B, and quiz 2, they're all due on the 5th of June. Okay, so all these quizzes are available to you, by the way. You can take them any number of times you want. Now, they're all going to close on the 5th of June, one day after the midterm. Okay, even so, if you look at this guy, if you look at the midterm 2, which is scheduled for 18 June, the 3 homeworks that correspond to this guy, they close one day after the midterm. Okay, so that's the deadline. Okay, this guy, the home final exam is on 2, and on the day of the final exam at 11:59 p.m. is when the homeworks will close. Okay, so more information about the midterm. Midterm begins at 10 o'clock and then ends at 11:30. Midterm 2 begins at 10 o'clock and ends at 11:30. Final exam is a 2-hour exam. It begins during the class time and closes at 1 p.m. So you want to be sure that you understand how the thought process that went into this. So there are quizzes and deadlines associated with the quizzes. They're all they're all uh, they're all working in tandem with the exam based off the exam dates and times. Okay, 3 big things do you want to remember are the exam times, and everything else is on the day of the exam. That's when they're due the homeworks, or one day after the exam. That's when they're that's the homeworks. Okay, and they're color coded by close date. Okay, questions, please. Questions so far. So the exams, you should be able to take it 3 times, and that's the reason why, even though this is a 1 hour 15-minute exam, okay, 1 hour 15-minute exam, if for some reason you found out that you took first 3 questions, you didn't do so well, you can immediately scrap that attempt and begin again on the exam. So there's an additional 15 minutes of buffer time if you change your mind and do want to take the exam second time or a third time. The highest graded attempt will be counted. Okay, so you can take the exam itself 3 times, but make sure, pay attention to the fact that it closes at 3:30 a.m. 3:30 a.m. This closes at 1 p.m. So there's a little bit of 15-20 minutes of extra time um, if you wanted to take the exam again. Okay, so that's about the schedule of the exams. Okay, and you know where to access the class videos, and you also know where to access the class notes. Questions, please. Questions so far? Okay, let's see if you can type in the chat window. What I want you to do is I want you to type your major. Are you in CPE or are you in Triple E? Okay, a lot of Triple E's and a handful of CPE. Okay, good. So as it turns out, this is a precursor course to 109. All of you who are in Triple E, you'll find that electronic engineering is all about being able to design semiconductor electronic components that use a lot of these diode circuits. Okay, when you're talking about diode circuits, when you're using MOSFET devices, okay, when you're talking about BJTs, all of these semiconductor devices, okay, they form the basic building block, and this course provides an intuitive understanding about how these circuits operate. So the expectation is that you have taken engineering 17 and Triple 117 courses, okay, advanced circuit analysis courses, okay, that help you understand these electronic courses. And speaking about engineering 17 and Triple 117, let me go to Moodle here really quickly and talk about the quiz 1A. Okay, if you look at chapter 1 on the Moodle page for this course, chapter 1 has a quiz 1A, which is in from a material that we cover in this class. It is from prerequisite material, circuit basics. Okay, so this is the material I expect that you already know from your engineering 17 and a little bit of 117, not a whole lot, but a little bit of 117. If you don't already, or if it has been a while since you took these courses, it's a good idea to start taking this quiz, brushing up the fundamentals that you need to brush up on. Okay, so sure. And it's also a good idea to test your access to the quizzes. So what I want you to do is, this is all available. All the quizzes are available to you already, but you should begin taking this quiz 1A as soon as possible, for more than one reasons: to test your access and also to test how fresh that concepts are in your mind. Okay, so that's the idea. So going off of your fundamental knowledge from engineering 17 and 117, we'll develop on that and understand electronic components that use semiconductor devices. Very interesting topic that uses MOSFETs, BJTs, and diodes. Okay, for CPE engineers, for computer engineers as well, a fundamental understanding of how some of these electronic components work is a valuable skill set, because as computer engineers, you'll be designing circuits, designing interface circuits. You'll be working on the intersection between software and hardware, and it is critical that you understand how the underlying hardware works. Okay, in addition to understanding the software when you're designing. But for electrical engineers, though, for electrical electronic engineers, it's a fundamental skill. Okay, questions, please. One thing I want to talk about when it comes to questions is there is no such thing as a dumb question as a wrong question. I want to encourage a culture of uh, freedom, and there's absolutely no reason for you to feel uncomfortable. You don't have to feel any inhibition to ask any question. I welcome all questions, and I kind of come alive when students ask questions. Okay, so now that you don't have any questions, why don't I ask you a couple of questions? What were your thoughts on the transition from in-person, in-person, face-to-face course to uh, online transition during the spring semester? How many of you found that useful? How many of you found that um, a little bit challenging?
Like it was a little bit of challenging in the starting, but now we are get used to it.
Yeah. The fact that you're not able to um, have a face-to-face interaction and not able to um, ask questions and participate in discussion as much is a little bit challenging. But well, for me, it was a blessing in disguise. I tell you why. Um, I, I was a little hesitant to going completely online, uh, but then like Zaid says, having recorded and uploaded lectures help. That exactly was my experience as well. I started recording my lectures as well and started posting them on YouTube, and that's when students found it a bit more helpful. Talking about that, by the way, I intend to make all of these notes and annotations. Uh, I intend to make them available on Google Drive. So when you see my, you don't have to be in a frenzy to um, copy everything or take notes frantically. All my annotations will be available to you sooner than later, and hopefully my video lectures will also be available as well. Okay, well, that's a positive thing. What else? So Baljinder says, I hope when we get back to in-person classes, professors can continue to record lectures and post them online. Me too. I like that. I like that opportunity, and it's um, a necessary step, and I will continue to do that uh, now that I have a hang of it. Okay, so good. So let's continue. Let's start with the basic topics, the signals and amplifier fundamental basics, fundamentals. Okay, and today, before the end of the day today or sometime before the lab time tomorrow, definitely before the lab time tomorrow, you'll have access to 108L as well. Okay. Here is the outline of the lecture. And by the way, all of this is available on videos as well. Okay. On video modal videos as well. Okay. So here is an outline of the topics. We are going to look at what a signal is, the different types of signals. There can be voltage and current signal, there can be sound and light, and a bunch of different varieties of signals. And the signals can be represented in analog or in digital form. So we look at that as well. Then we look at the Thevenin and Norton equivalent signal models. We look at the frequency spectrum of signals, how they are represented in the frequency domain. We'll talk about signal processing and also amplifier basics. Okay, when we send a small signal in and want to amplify the signal, enlarge it, um, there are different kinds of amplifiers possible. There can be voltage amplifiers, there can be current amplifiers, so on and so forth. So we'll take a look at all the different basics of all the different kinds of amplifiers, and then we'll talk more about that, and then summarize. So that's more or less the idea of what we will be talking about in today's lecture. Okay, signals, that's the first chapter from Cedrus method. So what is a signal? In its most basic form, anything that carries an information is called a signal. Okay, most signals include electronic waveforms, but they don't have to be electronic waveforms. They can be sound signals like doorbells, car horns, telephones, etc., or telephone ring. That's the sound signal. They can be even loud light signals like like um, uh, the like the fiber optic signals. Okay, optical signals that are sent via fiber optic cables, elevator signals, traffic lights, videos, so on and so forth. Any waveform, anything that carries some useful information is called a signal. Any medium that carries a piece of useful information is called a signal. So electrical systems typically use voltages and currents, okay, to carry information, but not always. Most oftentimes we see signal being carried as voltages, and there is an increase in voltage or a decrease in voltage that means something to us. Okay, in the digital domain, a 0 and a 1, they have some meaning. 1 means something, 0 means something else. Okay, so encoding information over voltages or currents, that there can be voltage signals or current signals, but it doesn't always have to be that way. There can, like I mentioned, fiber optic networks use light to transfer information. So there is a light signal, that's not a voltage signal. But for us, electronic engineers, most of the time we deal with voltages and currents, sometimes with light signals as well. Okay, then that's um, in order to be able to communicate using signals, we need sensors and transducers. Okay, sensors and transducers. Sensors change temperature, air pressure, etc. Microphone, sensors sense or measure is probably a better description. Sensors measure, okay, temperature of some real world quantity. Sensors measure a real world quantity. Okay, they it could be temperature, it could be air pressure, it could be, and they convert that quantity into a corresponding voltage or current signal. Microwave, for example, changes the sound waves into corresponding voltages. Microphones convert the sound waves into voltages. So there's a transducer right there, sensor. Okay. Similarly, actuators are on the other side, converting from a voltage signal to a real world signal. Is an example. There's an example. A speaker converts voltage signal into a corresponding sound signal. Okay, so there can be two different kinds of sensors and actuators. Okay, a motor translates an electrical voltage into some kind of mechanical signal. Okay, work. So all of that. So that's about how we sense and modify signals. We use sensors to measure their values, and we use transducers and we use actuators to change their values. Okay, so on two sides. Now, but not everything is a signal. If you think about it, a lot of noise, traffic noise that doesn't have, for example, a lot of useful information. Well, that's not a signal. DC supply voltages, okay, supply voltages, most oftentimes, they don't have any useful information. They're just there to provide operational power. They're not there to encode any signals. So DC power supply voltages, they're not signals, they're just power supplies, so on and so forth. So not all voltages are signals. Some of them are, many of them are, some of them are not. Okay, traffic, for example, is another traffic noise is another um, variable that is not a signal at all. Okay, so that's about signal, and that forms the basis for our understanding how a signal varies with time. That's something we care about as electronic designers. Okay, questions, please. Questions so far?
If we want to represent like DC signal on a graph, so it will be a straight line.
Yeah, yeah. DC signal will be usually a straight line. Okay, and on top of that, you can have a time varying AC signal as well. Okay, so anything that doesn't change with time is a DC signal. Okay, there is no variation of this signal with time. Any signal, on the other hand, anything that changes in whatever fashion with time, that's AC signal. It changes. It sometimes in a specific context, it's also referred to as a small signal, but in a different context. Okay, but signals themselves can be analog or digital signals. Okay, any signal that has a continuous change, it can take any value, infinitely um, large set of values. Let's say this is going all the way from -2 all the way to +5. There is no limit to what values it can take. It can take, for example, 1.00109, and it can also take 1.37987. So the range of values possible for an analog signal is infinite. There's no limit. On the other hand, a digital signal has very limited set of values. It can either be a 1 or 0 in most cases. Okay, so fundamental difference between analog and digital signals is that analog signals are continuous. These values are discrete. They're continuous in value and continuous in time as well. On the other hand, digital signals are discrete in value. Okay, digital signal cannot take a value of 0.009 because it's quantized. It's either rounded down or rounded up to its nearest integer. Okay, so that's the difference between analog and digital. So what happens is we most oftentimes approximate analog signals as a digital signal. So we like to round up analog signals into digital form because it's much easier to handle digital signals. Okay, so analog signals are continuous both in value and time. Digital signals are discrete both in value and time. They can be any value at any time. Analog clock, they can only be fixed. They can only have fixed values, discrete values at any given time. Okay, that's the idea, fundamental difference between analog and digital. So here is a question for you. The real world signals, the real world quantities, do you think they're analog or do you think they're digital?
Uh, uh,
Analog, analog, that is correct. Muhammad, Francisco, everybody, you're right. The sound waves, the volume at which I speak, the frequency at which I speak, it's not quantized.
of
I can lower and um, raise my voice without any quantization. In other words, it can take any continuous value. Sound waves, temperature, pressure, all of these are examples of analog signals. The real world, as a matter of fact, real world signals are all analog. Real world signals are all analog. Okay, microprocessor, computer is all digital. Okay, and naturally we need to have a mechanism to go back and forth between analog and digital signals. So if you can see, what is happening here is the blue wave shown here, the analog signal, is approximated using a digital signal here. So there are some errors. If you think about it, so this digital approximation, okay, is that's what it is. It is an approximation. If you lay it on top of the analog signal here, well, it's not going to be a 100% accurate representation. For example, here in this scenario, the actual real world analog signal, it goes up before it comes down. Well, that is not captured in the digital approximation here. Okay, so that's the nevertheless, if we can do a good job of taking enough samples here, we can make a reasonable digital approximation of the underlying analog signal. So this guy is analog signal, infinite values, and that is approximated using finite values here in digital. Okay, so it's always going to be an approximate representation of the underlying quantity. Okay, but if we do a really good job um, um, of doing the approximation, then we can be we can be assured, we can have enough faith that the approximation is good enough for my applications. Okay, so on the right is a digital waveform. On the right is a digital waveform, as you can see. Okay, approximating the underlying analog waveform. Okay, analog signals like the voltage above can be sampled at regular intervals of time. That is exactly what I'm doing here. So I'm taking the value of the analog signal at continuous intervals, at regular intervals of time, in order to convert from analog to digital. Okay, so if I sample at periodic intervals, then I get what is known as the digital representation of it. So in order to convert from analog to digital, I have to sample. Okay, so as you can see, there is going to be some rounding off errors. Okay, so fundamentally, converting from an infinite number of values in the analog domain into a finite number of predefined levels in the digital includes some rounding error.
I have a question, Professor.
Yes, please.
So before we said that the digital signal is rounded to either 1 or 0, but in this example, it's not rounded to 1 and 0 in this representation.
Yes, yes, thank you. It's a very good question. Okay. So here what is happening is, let's say we can still round it up to 1 and 0. Here is what I'm going to do. Okay, listen, there is 1, there is 0. Okay, how am I going to round this up to 1 or 0? Let's pay careful attention. Look at this particular value. Okay, is it closer to 1 or is it closer to 0? So 1 is right here, 0 is all the way down here. Okay, so let me make this a bit more clear. That way it's not ambiguous. Okay, now tell me, is it closer to 1 or 0?
1.
So I'm going to encode this bit as 1. How about this guy? So you can see that all of these signals are closer to 1. So I can round them all up to 1. Okay, so I can do something, a wave, something that looks like this. A digital wave using 1-bit representation will look something like this, because all of these are close to 1, right? All of these are close to 1. So all of these will be represented by 1. And this will all be represented by 0, so on and so forth. So if I'm using only 1 bit, okay, all of this part of the wave is approximated as 1. And all of this is approximated as 0, but that seems to be a very, very crude approximation, okay? Because I'm losing a lot of information. Instead of using just 1 bit, what I thought of doing is, well, I'll have a fixed number of levels. Let's say I have 3 levels, okay? Let's say I have 3 levels, tie this to that guy. I have 3 levels. Instead of 1 bit, I'm going to use 3 bits digital. So I'm going to call this as 001. I'm going to call this 010, 011, 100, 101. And this guy, I'm going to call it as 000, so on and so forth. Let's bring this down a touch. So that is going to be 110, 111. So what I'm doing here is, instead of using just 1 bit, like I showed earlier, which was very crude approximation, I'm using more than 1 levels, okay? So now, when I approximate a particular value, this particular value, for example, I'm going to round it up to its closest number, 101, or I'm going to round it down to its closest number. So in theory, digital values have only 1 or 0, right? So that means they're only using 2 levels. But if I want to make my digital signal more accurate, what I do is I increase the number of bits from 1 to 3 to 10, so on. By increasing the number of bits, I can increase the accuracy of the digital signal. Does that make sense?
Yes, Professor. Thank you so much.
Okay, so here we are using more than 1 levels, and therefore we are using 1 bit. That's the short answer. Okay, that's a very good observation, though. So I kind of implied that I tiptoed around it. Now, digital signals are used to represent analog signals. They can be discrete, like I said. Instead of having an infinite range of values here, I only have a limited number of values, okay, discrete set of values. Any analog signal is rounded to its closest digital value when converting to digital signal. Okay, so that's the idea of conversion between analog to digital signals. Okay, so analog, and here is fundamentally what happens. Let me do this. Let me, sitting inside, in between the extremes, is your microprocessor, okay, or a microcontroller. The brains of the CPU is all in the digital domain. The real world is analog, right? So what we have to do is we want to be able to convert the real world analog signal into a digital signal here, bits 0000. So we need some kind of data converter, analog to digital converter, when we are translating the real world analog signals into digital domain. Then we can do all our signal processing here. We can do all the signal processing and then convert it back to real world. Okay, that is what your iPhone is doing. For example, when you want to talk over phone, what happens is your real world voice signal is captured by the microphone and it is translated into a digital signal, ones and zeros, using the ADC. Then that is transmitted over the digital communication medium. And on the other end, out of the speaker, the digital signal is converted back to analog real world form. So this is a typical layout of the translation from a real world signal into a digital signal via ADC. Then most signal processing transmission, just about everything interesting is done in the signal, in the digital domain. And then it is eventually translated back to real world. Okay, analog to digital converters are used to convert analog signals to digital signals. As you can see, some information is definitely lost. Okay, digital to analog converters are used to convert digital signals to analog signals. No information is lost. Okay, so you're not losing a lot of information when you're converting. In theory, if you do a good job. Okay, one thing you want to understand, and let me make just one page here. Okay, so if you have an analog signal that looks like this, and you want to represent it using digital signal, just two levels, that's a very crude approximation. Instead, if you can express this using a digital signal that has more levels, okay, if you can express this using a digital signal that has more levels, okay, then what happens is this is a better approximation. Okay, so this is the analog signal, and this is the 1-bit digital signal, which is an approximation, but a crude approximation. It's 1 and 0. Okay, but this guy is, the number of bits is higher. Okay, number of bits is higher. So this is a better digital signal.
I
So
think
this
there's a
better digital signal. I'm sorry?
like there's a process named quantization, something like that. Is it?
Yes. There's an idea of quantization, which simply means rounding up or down. Okay, that's a little beyond the scope of this class. I can maybe spend a minute about it only to illustrate what the idea is. But let's say, let me copy this here, and let's see. Add a page. So let me talk about the idea of quantization. Okay, and I'm going to take the help of this guy. Paste. I don't know. Let's say here is my analog signal, some real world signal. Okay, that's the analog signal. And let's say I want to convert it to digital. And then what I'm going to use is I'm going to follow these lines. Take a look here, the ruled lines on the notebook. The notebook is a ruled notebook, right? I'm only going to use these as my digital values. Okay, those guys, those levels. So what I'm going to do is I'm going to sample at each instant of time, a bunch of different instants of time. 1, 2, 3, 4, 5, 6. So at any given instant in time, let's say at that particular instant, let's use this guy. Okay, at this particular instant, I'll pick something right here, this guy. This guy. Okay, at that particular instant, the value is right here. So the question I'm going to ask is, am I going to round it up or am I going to round it down? Okay, based on that, if it is closer to the upper level, I'm going to round it up. If it is closer to lower level, I'm going to round it down. Imagine like this is 5 and this is 4. A value of 4.327, when you're rounding it, you always round it to 4. If it is 4.87, you round it up to 5. So there is all this process of rounding up or rounding down is called quantization. Okay, when you're converting from a real value to an integer value, that's the idea of digital to analog conversion. That's the idea of quantization. So the bottom line is analog to digital conversion always has some rounding error. Okay,
If,
granted,
if it is
if
if it is
if you
4.5,
yeah, if it is 4.5, then you have to define what it's going to be rounded up to. You can in your algorithm, you can say 4.5 is going to, you can say 4.5, your value less than 4.5, round it to 4, greater than or equal to 4.5, round it to 5. So it depends on your algorithm. Okay,
there's no fixed rule for it.
there's no fixed rule. It's the way you design your analog to digital conversion. Okay, so the idea is if you increase the number of these levels, then it's going to be more accurate. Okay, it's going to be more accurate. So instead of rounding it down to 4, you can round this 4.325 to 4.5. Then the error is much less. So the idea is by increasing the number of levels or the number of bits, you can increase the accuracy. Okay, the rounding error will be reduced. Nonetheless, the rounding error is inevitable. Okay, that's your real world signal. There's going to be rounding up or rounding down. That's the process of analog to digital conversion. Analog to digital conversion always entails some kind of rounding error. You can increase or decrease the rounding error by playing around with the number of bits. Okay, questions, please. Other questions? Okay, so that's the idea of analog and digital signals. Let's see how far along are we now. The most important analog and digital signals that we encounter are voltage and current signals. So we want to understand these voltage and current signals shown as a Thevenin's equivalent here.
Professor, I have one question from the topic above.
Yeah.
It says like, if you go one slide up, I have one question.
Okay.
So it says in the bracket, like some information is lost, no information is
Yeah.
lost. So what does that mean?
Some information is lost simply means there is a rounding error.
Okay.
Okay. So take an example here. Take a look earlier. If you see, there is a rounding error. That is what it talks about when there is some information is lost. Okay. So voltages and signals are usually modeled with a Thevenin's equivalent. Okay. What is the resistance looking in to this voltage source? Okay. So that's the idea. If I were to stand here and look in to these two terminals, what is the resistance that I would find? Okay, if I were to look into these terminals, okay, what is the resistance that I would find across these two terminals? So that's the idea of, so voltage source always has an equivalent Thevenin's resistance. So this setup voltage source in parallel with in series with a resistance, that is called a Thevenin's equivalent. A current source in parallel with a resistance is a Norton's equivalent. Okay, so RS is used to model the source resistance here, the resistance of the source itself. Okay, so that's the idea of analog voltage and current signal models. Okay, we talk about this a little bit more when it becomes important. Okay, what we want to understand is any resistance, source resistance, like so, that because of that we incur some loss in signal. Okay, so I'll give you. Why don't I explain this to you? Imagine that there is no resistance here. Okay, there is no source resistance. Okay, there is just the load resistance that I want to drive. Okay, what would be the V output across the load resistance? What is the V output across RL?
Then equal to Vs.
It's going to be Vs. All the voltage that is coming out of the source is going to show up across the resistance here, correct? But in real world, there is no such thing as a perfect source. Sources typically have some kind of resistance associated with them. Okay, there is some kind of source resistance, and because of source resistance, when we use the voltage division method, the output voltage in the presence of source resistance is Vs times RL over RL plus RS. So some amount of Vs. So if this were zero, if RS were zero, okay, if this goes down to zero, then V output, the limiting case becomes V output is the same as Vs because RL cancel. If not, if I apply some voltage Vs equals to 5, only a fraction of that is going to show up on the V output. So if I apply 5 volts here, 1 volt is going to be dropped across RS. Only 4 volts is going to show up across the resistance R load. So there is some signal lost because of the source resistance here. Okay, some signal is lost when a load is connected. Does it make sense? So in order to make the loss minimal, what I want to make sure is that RL over RL plus RS, if I make this a really big number, okay, then V naught is going to be as close to 1 as possible. If I make this as close to 1 as possible, then V naught is going to see most of the applied Vs approximately. So in order for us to see all the applied signal, I want to make sure that this term, okay, this term in the denominator is very, very, very small. So for example, if this is 1 ohm compared to 1 mega ohm, so the overall term here, 1 mega ohm by 1 mega plus 1 ohm, these are just extreme cases just for understanding, is going to be approximately 1. And that is what we want. Okay, so the idea is by making the source resistance as small as possible out of a voltage source, okay, we can get a very good voltage division. A very little signal is lost. Okay, the opposite is true here. Okay, when you look at the current source, let me use a different here. The current source, the resistance RS, the goal is to have a lot of current flowing through this branch and very little current flowing through this branch. Does that make sense? So earlier what I did was, if I look at, let me go back to, let me explain the idea of source resistance. There are 2 resistances here, RS and V naught. Okay, my goal is that the applied signal here, most of it should show up here. So most of the voltage signal that I apply here should show up here. And a little bit, just a small amount should be lost in the source resistance. Okay, so in order to do that, make this very small and make this very large. Thus, most of the voltage that I apply here is showing up there. Okay, very little signal is lost across this RS. On the other hand, let's think about the current here. My goal is that the current that I apply as the input signal, most of it should go through this resistance. Very little should go through this resistance. So think of it this way. There's a lot of cars coming in this branch. And you as the traffic controller, you want to make sure that a lot of cars flow through this branch here and very few cars go through this branch. How would you go about doing that? Well, what you do is you make sure that there's a lot of hindrances, stop signs in this path. There's a lot of resistance. If you keep a really, really, really large resistance in RS and a small resistance, very few signals and stoplights in this guy, then most of the traffic is going to go in this. Very little traffic is going to go down this parallel path. That's the exact idea. If you want very little signal to be lost, you want to make sure that the source resistance is very large from a current source. This guy is large. You want RS to be large. You want RL to be small. You don't want any traffic lights or any stoplights in this road, and you want a lot of hindrances, stoplights, because you want very little current or traffic flowing in this signal, this path. Okay, so that's the idea. Different considerations when it comes to current sources and voltage sources. Okay, an ideal current, so an ideal voltage source has a really small source resistance. Okay, an ideal voltage source has a really small value. But an ideal current source has a really large RS. Okay, RS should be small for voltage source. RS should be large for current source. Does that make sense?
Uh, Professor, can I ask something, one question? Like
Yeah.
if we want something, like if we want current not to pass through RS, can we open it up, like open circuit, something like that?
This guy, as in
He,
you want to, let's see, you want to open this circuit, keep it open
yeah,
circuit
so
like so.
yeah,
Yeah, that would be your ideal case, right? Your ideal case would be a very large value here, meaning that it is infinity, a very large value. The limit of this, limit
mm,
RS tends to infinity, that's the limit. But ideally, it is not possible to have that. Real sources cannot have a really large open circuit. So mega ohms, giga ohms is what you can achieve ideally. Real
so
world. Does that make sense?
so like increasing the value of RS, like very large value of RS is equivalent to opening up the circuit.
Correct. If you have an infinite RS value, that simply means an open circuit, right?
Okay.
So that's correct. In the limiting case, ideal case, um, it's sometimes in your hands as a designer, sometimes it is not. So there are other variables that control RS. So if it were completely in your hands, you would ideally make it infinity, this RS here, okay? You would ideally make it open circuit and make it infinity, but that's not completely in your hands. There is, you can to some extent tune it, but not fully, okay?
Okay.
Other questions, please. That's a good question. Okay, so frequency spectrum of signals, typically what happens is your signal has more than one frequency. If you look at this sine wave here, there is just one particular frequency. There is one time period, and 1 over that time period will give you frequency. But why signals or real world signals typically, they rarely have one frequency. They have more than one frequencies in that signal. Okay, so arbitrary signals, real world signals, consist of more than one frequencies. They have many frequencies associated with them. Okay, and then the frequency domain. So in the top, we have seen time domain, time on the x-axis, and the voltage on the y-axis. When you're representing it in the frequency domain, on the x-axis, your variable is frequency. It could be radians per second, or it could be even hertz. Okay, and along the y-axis is the volts. Okay, so what it does is it tells you that a lot of signal voltage is in the low frequency range, and very small signal power or signal voltage is in the high frequency range. So this kind of tells you the distribution of frequencies. A big chunk of frequencies are in the low range, okay? And the high frequencies shown towards the right here have small amount of voltages and power. So this tells you um, uh, the distribution of the frequencies and their voltages in your spectrum. So that's the idea of spectrum. Questions, please. Okay. All right. So that's the idea of frequency of spectrum. So take a look at this guy. This is a very clever, a wonderful imaginative aspect of repeating sine waves. Okay, repetitive waves, periodic waves. Look at this guy. There is a square wave. Let's say I have a square wave of a particular frequency, one frequency, square wave of one frequency. There is one frequency, right? 1 over t will give you the frequency of this guy. But the really magical, the magic of Fourier transform, or what Fourier found was that any wave that is repeating can be expressed as a sum of bunch of sine waves. Okay? You see what is going on here? One square wave with one frequency that can be expressed as a bunch of sine waves, with different frequencies. Okay, so here is more or less the idea, and you can YouTube this if you want to. So, in order to generate you could even do this in MATLAB. You could simply create a sum of bunch of sine waves, and as you increase the number of sine waves, you'll see this getting closer and closer to the square wave. Okay, so the idea is Fourier transform is the way of representing any repetitive waveform using a sum of square waves. Okay, a sum of sine waves. So you start off with a sine wave first. Let's see. I don't know. Let's say I start off with a sine wave that looks like so. Notice the sine wave has the exact same frequency as the square wave. Then you duplicate that, okay, oops, in a much smaller value, okay, and 3 times the frequency. And okay, so if you were to do something like this, okay, so that is represented here. So let me color code them a little bit here. Okay, so this purple wave here, that's this guy. Then there is the little wave shown here, okay, in red. Okay, that's more or less approximately 3 times the frequency. So that's the 3 omega naught. And then it's only 1/3 in size. This guy is so wide, while the sine wave shown in red is smaller in amplitude. So that's 1/3. Okay, so that's 1/3 over here. And then there is so in a similar manner, you can add a frequency that has 5 times, add a sine wave that has 5 times, and only 1/5. So in other words, when you add up all of these sine waves, this guy, the red one, and another sine wave with a green color, so on and so forth, take different sine waves of different frequencies, add them up carefully, you can approximate that to be a square wave. That's the idea. So if you look at the frequency spectrum, what the frequency spectrum says is there is going to be one sine wave with an amplitude of 4V over pi. Okay, and there's going to be one sine wave with a 3 omega naught frequency and some amplitude. There is a sine wave of 5 times that frequency and some amplitude, so on and so forth. So if you add all of these, so each of these lines here is one sine wave. So when you add 1, 2, 3, 4, 5, a bunch of sine waves, you get a square wave. The more number of sine waves you add, the more closer it is going to be to the square wave. So that's the idea of Fourier transform. You can approximate any repeating wave using a sum of bunch of sines, S-I-N-E, sine waves. Okay, in this example, I have shown you how to approximate a square wave using a bunch of sine waves. So that's a wonderful observation, and that divides the available spectrum the available that explains that makes it easy for us to visualize the available spectrum in a given repetitive way. Okay, so this guy is called the fundamental frequency. Okay, and all the multiples of that are called the harmonics. In this case, there are odd harmonics. 3 times fundamental frequency, 5 times fundamental frequency, 7 times fundamental frequency, 9 times fundamental frequency, so on and so forth. So it's easy to see. You expect this to be 1/9 4V over pi with 9 times omega naught, so on and so forth. Okay, the higher frequencies with reducing amplitude are called harmonics, and the fundamental frequency omega naught, that's the fundamental frequency. Questions, please. Questions so far? Okay, so that's the idea of frequency spectrum of signals. Intuitively, what I want you to understand is any repeating wave can be expressed as a sum of sine waves. So that's exactly what is shown here. Each line here is one sine wave. Okay, the length of the line represents the amplitude of the sine wave, and the location itself represents the frequency. Cool. Okay, so that's the idea of square wave in its spectrum, frequency spectrum. Okay, once we know that, we are able to talk about signal processing. Much of electronics focuses on the use of MOSFETs. If you have a really small signal, how do you amplify it? Okay, for example, let's say I have a signal coming in from a satellite. Okay, signal coming in from a satellite to my antenna. Okay, that typically is in a very small value, nanovolts, microvolts range. Well, that is really small for me to decipher. So what I have to do is I want to convert it into enlarge it into meaningful range. That is the process of just like I'm doing here. I'm amplifying, I'm zooming in, I'm amplifying. That's exactly what I need to do to amplify or magnify the signals. So that is one example of signal processing. Okay, most of the signal processing is done in the digital domain these days because that is more accurate compared to the analog signals. All right. Now, sorry about that. Now, so common signal processing functions include amplification, filtering, data conversion, so on and so forth. Okay, so there's a lot of noise. There's a lot of high frequency noise that you want to filter out. How would you do that? So that's done using signal processing as well. So in other words, signal processing is starting with an input signal and extracting and actually massaging it in a way that makes it more useful to you. That's the idea of signal processing. Okay, filtering out unnecessary components, filtering out or amplifying the necessary components, so on and so forth. Other common functions performed by electronic circuits are converting from analog to AC to DC for power supplies, phase locked loops, comparators, so on and so forth. But then that's just an understanding. That's just a list of signal processing techniques. Okay, signal processing functions. Questions, please. Questions so far.
Can an amplifier decrease the voltage, like make it smaller?
Yeah.
Yes, it can. Okay, if the amplifier increases in magnifies in size, then you say the gain of that guy, the gain, let me not be AV, the gain is greater than 1. Okay, if on the other hand, if the opposite happens, isn't that a good question? Isn't that an excellent question? If on the other hand, the opposite happens, so if the signal is diminished in size, then you say the gain here is less than 1. Okay? So it is possible for an amplifier to reduce the gain or to have a gain less than 1. That's a good question. Other questions, please. Okay. So now, here is a typical example of a electronic system that we already saw. We saw this, didn't we? We saw that there is the real world on one end, okay? And then there is the microprocessor, digital signal processing microprocessor sitting here. That microprocessor is handling all of your signal processing, okay? But then there is the sensors that are reading the value of the real world, converting it to digital domain, okay? Digital. All the signal processing is done in the digital world, and then you have to convert it. Like I mentioned, there is a phone here. On one end, there is a telephone. So that is my crude representation of a telephone. The telephone signal, the voice signal that you do is analog. That has to be converted to digital signal. It has to be converted to digital and then transmitted over the digital communication medium. And later, on the other side of the phone, it has to be translated back into a sound signal. So all of this is fundamentally the basic architecture of an electronic system. Okay, so there is analog to digital driver, digital to analog conversion system, so on and so forth. So analog and digital electronics can be amplifiers, there can be filters, comparators, buffers, current voltage converters, analog to digital converters, wave shapers, voltage limiters. There's a whole list of analog or digital signal processing. Remember, what is signal processing? Signal processing is simply converting the signal from the way it is into the way that you need. Okay, what if you want to magnify it in size? What if you want to filter some components out? What if you want to suppress some aspects of it? So on and so forth. Okay, so there is a whole host, a list of analog digital signal functions that we can do. Okay, so questions, please. Questions so far. Okay, so I continue to, I like the discussion that you spurred in the class. It's very good. And I encourage you to continue to do that and do more. Yes, question?
Yeah, like there's one question on the chat, like what is transducer?
What is transducer? Okay, so where is it on this slide at all?
Yeah, transducer. Yeah, it's on this the slide you were present.
Right here, right? Transducer. It typically is converting from one form of energy to another form. Typically converting from a real world to a voltage signal. Okay, so pressure converted to a corresponding voltage signal. Okay, think about this. Let's say there is a sensor in your car, right? There is a speed sensor, airbag sensor, right? What is it doing? It is translating the accelerometer. What it is doing is, it is keeping a tab, it is sensing your speed, okay? And then that is connected to a circuit, the accelerometer, okay? So if you think about it, on one side, the accelerometer is measuring the speed, and on the other side, it is translating the speed into a voltage. So any device that does this converts from one form of energy into another form, from a velocity signal to a voltage signal. That's a transducer. Anything that converts a sound signal to a voltage signal or a current signal. That's a transducer. Okay. On the other hand, you can also have conversion between a current signal to a sound signal by a speaker. That's also a transducer. Do you see what I'm saying? Any component that translates from one form of energy into another form, typically voltage or current, that's a transducer.
I have a question. Like if we talk about electric motor, it converts electrical to mechanical. So,
Yes.
so is there any component in motor that converts it, or we will say that whole motor is a transducer?
Well, the underlying principle is based on having a metal wire in the presence of magnetic field. But the operation is based on transducing um, from a magnetic energy, electromagnetic field into some kind of force. Okay. So other questions, please. So at the heart is a transducer. At the heart of a motor is a transducer. Other questions, please. That's a good question. All right, we'll come back and take this up from here. We'll talk about amplifier basics. Between now and tomorrow, you want to try your homework. And see if you have access. That's number one. Number two, look out for an email about how to access 108L. I'm going to make that available to you sooner than later. Sorry for going over the time by around 2-3 minutes. Thank you. I'll see you folks back tomorrow.